In this example, the trolley is held in place by a force pulling it upwards parallel to the ramp. If we know the weight of the trolley and the angle of the ramp, we can work out how big this pulling force needs to be. We can see that the angle of the ramp is 30 degrees above the horizontal. The weight of the trolley is 8.2 newtons. There are three forces which act on the trolley. The weight, which of course acts vertically downwards. The pulling force P, which acts up the slope. And the normal reaction of the ramp on the trolley. In reality, this is shared between the front and back wheels, but for simplicity we've just shown it as one force N. This diagram shows the forces which act on the trolley. We know the weight W and we want to find the force P and the force N. If we wanted to, we could find the horizontal and vertical components of both P and N and work out the answer that way, but that would involve unnecessary work. It will make life easier if instead we find the components of the weight which act parallel to the slope and at right angles to the slope. It can cause confusion if we mix up pictures of real objects such as the trolley with vector diagrams, so I'm going to draw a separate vector diagram to show the force W. This arrow represents the weight W. I haven't drawn it to scale because I'm going to use trigonometry rather than measurement to find the values of the components. This is the direction of the slope, and the force W has components parallel to the slope and at right angles to the slope. To find the component parallel to the slope, I need to draw in this line to complete the triangle. And this side of the triangle is then the component of W which acts parallel to the slope. And of course it will be acting down the slope. This side of the triangle must represent the component of the weight which acts at right angles to the slope. A little awkward drawing the two arrows on top of each other, but we'll do our best. So there we have our two components. The angle at the bottom of our vector triangle must be the same as the angle of the slope, which is 30 degrees. To find the size of our components of W, we need to use trigonometry. If we look at our vector triangle, we see that this component, the component that acts down the slope, is the side that's opposite to our 30-degree angle. So remember our trigonometry. Opposite divided by hypotenuse is equal to sine of 30 degrees. So the opposite divided by W would be sine 30 degrees. So that must mean that the opposite side must be W sine 30 degrees. And to find the value of our other component, in the triangle this is the adjacent side. Adjacent over hypotenuse is cosine of 30 degrees. So The perpendicular component divided by W is cosine 30, so this component of the force must be W cosine 30 degrees. If the force P wasn't there to hold the trolley in position, the component of the weight acting down the slope, W sine 30 degrees, that would cause the trolley to accelerate down the slope. But in our example, the force P is present and we know that the trolley is held stationary. In other words, the forces must be in equilibrium. So the force P pulling up the slope must be equal to the component of the weight acting down the slope. So we can write the equation P equals W sine of 30 degrees. And we know that the weight, which we measured, was 8.2 newtons. So P equals 8.2 times the sine of 30 degrees. So we take our calculator, 8.2 times the sine of 30 degrees, which is 4.1 newtons. And we can also work out the size of the force N. Since the trolley isn't sinking into the slope and isn't jumping off the slope, the component of the weight acting at right angles to the slope must be equal to the reaction force N, which the slope puts on the trolley wheels. So we can write N equals W cosine 30 degrees, which is 8.2 times the cosine of 30 degrees times the cosine 30 degrees, which is 7.1 newtons. And we can see that the reading on the force meter is 4.1 newtons. Haven't fiddled it, honest.